How to catch light in a bottle. Let's consider how to measure wave-like phenomena using an oscillatory bottle. In many situations, given the various couplings possible, this translates to the capability to capture small measurements in a coupled time integrable system or apparatus by using time as a lever. This type of apparatus allows one of the most sensitive techniques for performing detection. This is done with gravity wave detection with an interferometric configuration, for example. Consider the damped-driven oscillator with noise fluctuations. Let's determine the minimum detectable force that the system can provide. This is the scenario with realistic noise fluctuations that provides an accurate limit to the sensitivity of measurement in general. Let's start with the oscillator ODE with added noise fluctuations term F sub F of L. See the next equation.
Where the steady-state result from before, without fluctuation noise forces, was x of t approximately equals b the cosine of gamma t plus delta. Is there still a steady state but with a slightly more general form? First consider that the amplitude relaxation time is given by tau sub m equals 1 divided by lambda, and we are assuming that the intention is to do precise measurements, so we seek a minimal damping, thus a maximal relaxation time tau sub m. Thus we have a relaxation that is effectively steady state compared to the time of measurement, and the time of the f of t effect meant to be detected. What results is the need to do a statistical analysis on the statistical criteria for the determination of the excitation of an oscillator by an external force. As was done by Brzezinski in an appendix with that title, see Book 1 in description for details, where see the equation shown. The assertion of a detection event will be a probabilistic one, where the probability density of an arbitrary distribution of amplitudes of oscillation after event time tau hat can be shown to be. See the next equation.
Where see the equation shown. If we assume just thermal noise, we then have, according to the thermalization temperature T, the following: sigma squared equals K sub Bt divided by K, where omega sub 0 equals the square root of K divided by M. We then get. See the next equation. Thus, if we start a detection event with A of 0 approximately equals 0, and we see the amplitude grow in time tau hat such that A of tau hat is greater than A of tau hat sub 1 minus alpha, then we have with probability or reliability 1 minus alpha that an event has occurred. From this we see that the minimal detectable force is roughly the same regardless of initial value of the amplitude and has the form. See the equation shown. Thus, the maximal coherent observation time possible gives the largest tau hat and thereby the minimal force detection according to. See the next equation. Thus, to catch light in a bottle you need to have a lengthy observation time.